the op-amp testing portion. Now, first of all, JF Technology. Yeah, so this is the company that I am working in. JF Technology is an umbrella company for many subsidiaries. So as you can see here, we have JF Micro Technologies Berhad. This is established in 2005, and then we have JFong Technologies. These two actually they also do business with the semiconductor industry, semiconductor factories in particular, to provide contactor solution. Contactor solution is basically providing the electrical connection between an IC and the board and a PCB that sits on the tester. I will talk in more detail what is this PCB and tester, but basically JFong Technologies and JF Microtechnology, they manufacture and design contactor solutions. Then we have this JF International. Now this one is basically a subsidiary that is set up in China, basically to cover the Chinese market. As you know, in China, this semiconductor industry is booming, so we are taking advantage of that by setting up a subsidiary there to service the Chinese market. Now, this is where I come in, JFTest. JFTest is a complement of the contactor solution. We provide the electrical solution. That means the test solution for an IC test, which consists of the test program. So there is software. You need to be a good software programmer, as well as you need to be a good PCB designer. These two skills are required. Okay, so basically, test solution involves the software as well as the PCB solution, and then you need to have a good critical thinking, debug problems. You know, when your software has been written, your PCB has been created, so you have basically two kinds or two possible problems that you can, sources of problems that can occur either from your program or your PCB. So you need to have the skills of how you zoom in into the root cause of the problem and in the quickest manner. Okay, so I'll talk more detail about that job function. But basically, JFTest is the one that will provide the IC testing course. And this is the factory, or this is the company, and it's located in Kota Damansara. This is the address here. This is the founder, Dato' Fong Wei Kuong, and our CEO, Dylan. Now, a lot of y'all understand the term IC, right? Integrated circuit. So y'all have probably seen also these ICs. You've probably seen it in the labs. Now, what are these for? So these companies in this semiconductor space, they actually design this IC and then they manufacture. So a lot of these ICs, for example, go into applications like your handphone, okay, your mobile phone. If you open up your mobile phone, you'll see a PCB and a lot of ICs sitting on the PCB, soldered in. Okay, so all these ICs serves a purpose. Okay, you have some of them for the processor, the brain of the phone, for digital baseband processor. Basically, the signal that you receive is then down converted to a baseband frequency, and then it's converted to digital for processing. And then the front end, which is the RF transceiver, where the transmitter and the receiver components will sit. So your RF signal comes in to this component, probably the amplifiers within this component for transmission as well as for reception. So you got different ICs for different purposes, and different companies have different expertise to provide the various functions that is required inside such an application. And it may be also inside a laptop. You have the processor. You can also have a power management unit. The power management part of the application like a phone or laptop or any other electronic device is the part that provides the voltage supplies to the IC and manages the supply so that it's stable. So this is basically an overview of the application of integrated circuits. They come in many form factors. Okay, you have the typical one. This is what I've been working on many years ago, the dual inline package. And then you can see here at the end, we have they have shrunk down to wafer level CSP. Okay, so the form factors, from large to small, and there are various other kind of packages in between. So many kind of packages in the industry. So these packages are actually defined by the end user. Okay, what kind of application and what kind of density they require on the PCB board. So the higher the density, the smaller the package. Okay, so if they're not worried about density, they can go for bigger package. So it really depends on the end user requirement. Many companies in Malaysia, I think there are about 40 or 50 multinationals who are doing who are manufacturing semiconductor circuits in Malaysia. They are mainly from the West, in Europe, US, or some in Japan. Okay, so a lot of these companies are operating mainly, as you know, in Penang. Penang is our Silicon Valley. And then you have some in the center of West Malaysia. You have some local ones like Kasem and Unisem who are contractors for the multinationals. And then we have in the south side, we have like ST Micro, Infineon as the major semiconductor MNCs. Okay, then we have service providers for the semiconductor factories, like local ones like Test Hub, which is in Malacca. Then you have, just now I mentioned Kasem, also a test development entity. Then of course there is us, TestSense. So Malaysian company, you can see here Test Hub, Kasem, TestSense, and Xperia. Okay, this Xperia is in Penang. We are in KL. Test Hub is Malacca. So it depends on where you stay, you can work in these different companies. Okay, Kasem is in Ipoh. Testolve is not Malaysian, it's Indian. Okay, so they are also based in Penang. Now, I will now explain the basic manufacturing process that an IC will undergo. Okay, so from design phase. So the concept and the design is the first one that happens in an IC life cycle, and during that time, the marketing people in this company will go and approach the end user and ask them what is the application, okay, and what is their technology roadmap. Technology roadmap means in the next 5 years, how will they see their application change? So when the company design the IC, they will take that consideration of the evolution in the next 5 years into the IC design. Okay, so if that IC design is accepted by the end user, then the IC designers will start to develop the product. Okay, they will use tools like Verilog, HDL coding, real-time logic simulation, and so on. So once after design is done, then that will be followed by wafer fabrication. Wafer fabrication normally is done by foundries, the wafer fab foundries, and there are about over 100 wafer fab foundries in the world. Okay, so the biggest one is in Taiwan, Taiwan Semiconductor Manufacturing Corporation, TSMC. Okay, they are the most advanced and biggest wafer fab. Then you have also MNC wafer fab like TI, Intel, ST, and so on. And then you have SMICs, which is Shanghai based wafer fab. So there are many wafer fab all around the world. And if you are a lone designer, or let's say you are a designer in a small company, you can send to people like TSMC or UMC in Taiwan to fabricate your wafer in large volume. After fabrication of the wafer comes to your factory. What do you do? Then you will a wafer will consist of many IC. Okay, so this IC need to be then segregated or cut out. Okay, or we normally call it in a sawing process. And they will be cut out and then they will be packaged into the whatever form factor that is required by the end user. Okay. Now, in this part of the manufacturing process is called the front end process. The front end. So this is where test engineers come in. After packaging, the obvious step is to test the device. Why we test? We want to make sure that the IC functions after all this processing. Okay, the wafer, the IC may be good during the wafer fabrication process. Then during the IC assembly, something may go wrong, and we need to test these devices out thoroughly to make sure they are still functioning per their data sheet. Okay, so this is our job. We need to develop the test solution to check the functionality of the IC that's coming out from the assembly line. But there is also another test function here. After wafer fabrication, we also can test or probe those wafers. Okay, so there are two places where we do testing. One is at the wafer stage, and the other one after the packaging. Okay, some people do both. Some people do only one. Okay, some mostly will do only after packaging. Some will also test at wafer, and then they will also test after packaging. So this philosophy of testing at wafer and at packaging, or we call this final testing, is depending from company to company. So after testing, you will obviously get good parts. That means parts that meet the datasheet requirement, and parts that fall out. Okay, fall out means they don't meet the datasheet electrical specs. Then at that stage, those fallouts are checked out and validated as genuine, or they need to be checked out very thoroughly to make sure it's not a design problem. Okay. Now this is still during the development phase of the IC. Okay, so we need to check whether the IC has an inherent problem. I mean, those failures are showing something that is inherent in the design, or is it something that came from maybe from assembly or fabrication. And then a qualification process. So before we actually hand over the IC for large volume manufacturing or high volume manufacturing, we need to do an infant mortality check. Infant mortality means we want to remove those IC that if it goes into the field for the first few months, it doesn't fail. Okay, imagine that you buy a new phone. After 1 month, the phone tak boleh pakai. Why? Because one of the IC is dead. That is called infant mortality. You want your phone to work for years, right? Not for 1-2 months. So that's why the company will do an accelerated lifetime check by burning in the parts. They take a sample of the product, they put it into an oven, and they will exercise the IC electrically for maybe 48 hours or 96 hours, depending on the application. And then the IC will be removed from the oven and then tested to check whether it's still functional. So that check is done, and if all 100% of the IC is working, then they can go on the next step of sending the part out for manufacturing. Okay, then it will go into a factory, and a lot of the factories here in Malaysia will do the final testing in high volume. So in short, this is the life cycle of an integrated circuit. And our area of expertise is the test engineering, where we produce the test program and the test PCB to test the ICs. Okay, all these other functions are done by other engineers. Design done by design engineer. Wafer fabrication, we have wafer fab engineer. We have packaging engineer for assembly. Then the test engineer falls in this area. Okay, so if you all have any questions, you can always stop me and ask those questions. So finally, we have high volume production. So after the product has been approved, okay, and it will be sent for high volume, and this is where the company will start making money lah. So they will start selling the product to the market. Okay. So now I will focus on that area called test engineering. What is this test engineering function? First of all, before I talk about test engineering, why we want to test the IC, right? So you all might be thinking, why don't we just manufacture the IC and then we send out to the market? Why test? Test seems to be an overhead, right? Because when you create something that is designed correctly, why do you need to test it? Because you designed correctly. Okay, so let's say a smartphone is costing, the cost of an assembled smartphone is USD 100. If one of the IC in this phone is bad, you will throw the whole smartphone, okay, the whole PCB, okay? But if the IC was tested before you assemble in the smartphone and the IC only costs $1, you lose $1. So imagine, which one would you rather do? So the smartphone manufacturer will say, I want all the IC that I'm going to use to be tested. So this is demanded by the industry. Okay, so they say you have to send me only tested good parts. Don't send me untested parts. So that's why test engineering is a function that will never go away. Okay, some people say it's an overhead, but actually today it's becoming more and more important. Why? Because the IC is becoming more and more complicated. Okay, more and more complicated, you need to test it more vigorously. And then the test also produce a lot of data, parametric information that the designers can use to further improve on further other derivatives of those IC. Then there is what we call a trimming process. A trimming process actually improves certain electrical parameters during testing. Okay, so when you fabricate the device, maybe the spread or the distribution of a certain electrical parameter is quite wide, with high, with the sigma being very low, and the low performance indicators. Then in that case, there is a process in test that's called trimming that will adjust those values or those electrical parameters to be to become in a tighter distribution. Okay, this is called trimming process. So the test engineering development. Now, very specifically, I want to talk about test engineering development. Okay, there are many functions in test engineering. One is just being a test engineer that just receives the test solution from overseas, and then they will just like just jaga the solution. Now, basically, they will just maintain. Okay, any problem, they will just report the problem back to the headquarters, either in US or Europe. But today we're trying to change that. We want to do development here. We want to do the actual development of the test programs and the PCB here. Okay, there are some companies already doing that, but we want that to grow. We want to show that Malaysia can do this test engineering development. So in the past, this job is normally close to the design side. Okay, where there's IC design, you have test development engineer. But this MNC here in Malaysia, as you know, is all back end, mainly in the manufacturing or in the high volume production. So there is no IC design. IC design is done in the US or Europe in the headquarters. So test development, we are trying to grow that function within the semiconductor industry, and what is the process that's involved in test engineering development. So the first thing that the test engineer will do is test plan generation. And then you will need to design the test circuit, okay? And then it will be sent for the PCB layout, will be sent for fabrication. Then we have the test engineer will do test program development. They will develop a test program that will contain all the test functions that is required to be tested. Then once you have the test program and the PCB, these two will need to be debugged because these are new, and we need to be debugged to make sure that it functions well. Okay, so the test engineer will go through this process of debugging, and then he'll need to correlate the electrical test parameters, the reading, the results that's obtained from the tester with the bench. So normally the application engineer will say, okay, this is the result I got on the bench, and you make sure that tester also got the same result. So that is called the correlation phase. So once the test program and the PCB is working, then it goes for qualification. That means it will run a higher volume of device in an automated manner using a handler, and we'll look at what are the outcome, like the yields, how many parts are good. Let's say I test 1,000 devices. How many parts are good? How many parts are bad? Okay, so this is the qualification process. And then in this process also, you fine tune your program to make sure your yields are better. And then once that's done, then it's sent to the factory, for high volume manufacturing. Okay, so the test development engineer play this role. Today, if you work as a test engineer in some of these factories, you only play this role. So what we would like to do is have this doing more value in test engineering, that means doing development work. So the test plan, okay, like you can see here, this engineer is developing a test plan that every test, there is always all the pins of the devices you need to provide. What are the voltages that you're forcing, okay? For continuity, let's say what you're doing for every pin. For leakage tests, how do you condition the pins, okay? For, let's say, for particular pins, what do you do for leakage checking, okay? So this is like an example of a leakage test plan. Then you need to be able to design the schematic. This is an example schematic of a device that an engineer has worked on, and then he will do the layout, okay, the PCB layout. So the next step is to do the test program coding. So he will develop the test solution, a test program, and for this, the engineer need to be familiar with the tester that he's using. So in this particular case, this engineer is working on one of the industry testers called the 93,000, and this is an advanced test tester. Then, as I mentioned, once you have the PCB and the test program done, normally when they send the PCB for fabrication, it takes anytime between 4 to 6 weeks. So during the 4 to 6 weeks, the test engineer can create his test program. So by the time the PCB comes, he will put it on the tester. So you can see here the background this is the test head. The test head is the tester that contains the test instrumentation. When I say test instrumentation, it means the DC source, the voltage source, current source, AC source, arbitrary waveform generators, digitizers, all that are inside the test head. And all these instruments are controlled by software, by the test program. So the test engineer will debug using tools available in the tester. Like this is a tool that captures the digital data that's coming out from the device. Okay, like the clock frequency, is it correct or not? The derivative of the master clock, okay, maybe the synchronous clock and so on, the frame sync and so on. They will do the debugging to make sure that the device outputs the correct pattern, the correct signal. Analog signals are captured and analyzed in time domain as well as frequency domain to make sure that they meet the required specs. Example for frequency domain specs are like signal to noise ratio, total harmonic distortion, all that is checked, which is a typical spec for digital to analog converters. Okay, so once he's debugged his program and let's say the program is good on a few devices, then he'll need to test more devices in an automated fashion and collect the data and make a cumulative distribution check. You know, this cumulative distribution check is also, the test engineer will need to be able to analyze the CPK, you know, the distribution. So every test, there is always a lower side limit, upper side limit, for example, and then you check the distribution. Like in this case, you can see that there is a tail that goes across the upper side limit, meaning that all these devices will fail. Okay. So he will need to find out the reason and see how he can shift this distribution more towards the center. Okay. So the automated testing of higher volume of parts is done by hardware called the handler. Okay. This handler actually is like a robot. It picks the devices, puts it into the test site, and then the tester will test it. Then he'll take out the device and put it onto this area for transporting to the output stage. So here is where at the output side, it will be segregated to good devices and bad devices. So this is the high volume manufacturing that is done after the qualification process. Okay. So you have seen so far the main job function or the process the test development engineer will need to perform. So in order for him to perform those functions well, what skills does he need? Okay, for test plan, you need to have test development process flow and project management. So for this whole process flow, he needs to have a total understanding of each and every one of the steps. Okay, he will need also to be a good project manager. He needs to establish clear project deliverables. What is project deliverables? So a customer will come to JFTest and say, hey, I got this product A. I need to test it in this much time. Let's say I want to test product A in 100 milliseconds per product. So the test engineer will need to develop a solution to provide that kind of to hit that kind of targeted goals that the customer needs. Okay, that is the deliverables. Okay, and then for that, the test engineer will need also to consider what is the budget and what are the timeline required. Okay, the customer say, okay, I need this by in 4 months time. Then they must make sure that they create a good plan to hit that timeline within the required budget. And then he must then execute the test development task. according to best industry processes and practices. So in JFTest sense, we are engineers with many years of experience, and we've been using industry best practices to do our test development projects. Of course, the engineer will need to track the projects to ensure the tasks are executed well and within timelines. He tracks and he will communicate the status to the stakeholders. What is stakeholders? Are all those managers and the customer. And then you need to plan each of the tasks and make sure that the risk management is taken into account, meaning that obstacles and countermeasures must be thought of before executing the project. So this is an example of a project plan. Okay, it's like a Gantt chart, and the test engineer will come on with this and then use this as a tracking mechanism. So on the technical side, the test plan and device testing methodology, this is a very important knowledge that the test engineer must have. He must be able to create test plans. He must be able to understand what kind of methodology is required in order to meet the testing requirements of the device. Okay, so basic knowledge of analog, digital, and mixed signal test methodologies. So analog, you know, digital, you know. Do you know what is mixed signal? Mixed signal is actually the combination of analog and digital. So some devices are just analog, right? Op-amp, analog. Then NAND gate IC is digital. But a digital to analog converter is a mixed signal because there's digital input, analog output. Okay, so that's what we term as mixed signal device. So the test engineer must be able to understand what is the requirement for an op-amp testing, what is the requirement for NAND gate testing, and what is the requirement for mixed signal testing. So then he will design the test to achieve best possible test execution time. So very important to remember here that we are doing high volume manufacturing, meaning that in automated test, the test time is very important. You cannot take too long to test a device. You take too long means that means the cost of test is high. Okay, so manufacturers want the cost of doing tests to be as low as possible. So execution time is one of the critical factor. Just see it as, okay, in 1 hour, how many parts can you produce? The more parts, the better, right? In order for me to produce more parts, I need to have a shorter test time. Or I need to have parallel testing. What is parallel testing? It's also called multi-site testing. That means I can test at one go, I can test 4 devices. That is quad site. So now I got 4 device output from one test execution compared to just one device. Okay, anything that increases throughput will lower down cost of test. And then of course, precision and quality must also be followed. And must be able to apply automatic tester resources. So the test engineer must be familiar with some of the industry testers that use, maybe a 93K or an Eagle tester, okay, to achieve the desired outcome. Then he designs the test PCB, keeping in mind the effects of stray capacitance and inductances on that signal. So PCB design is a skill where when you do the layout routing, you must take into account resistance, capacitance, and inductance. What are the effect of those capacitance and inductance on the signal? Okay, for example, if I'm sending a high frequency signal, I want to make sure that the stray capacitance on that trace is as low as possible. Okay, otherwise it becomes a low pass filter. So these are the thinking that the test engineers must have. Okay, so they must be able to design circuits for filtering, amplification, and impedance. Okay, so all this design of circuits to condition your signal that is going to the device and from the device is very important. Okay, sometimes you need to have a buffer to buffer the high impedance output of a device when it sends a signal to the tester, or the other way around, when a tester sends a signal to the device, then you need to have a filter probably, to filter out other frequency components. So this is the test plan, an example test plan. So every test, the test engineer will need to create a test plan before he do the test programming. This test plan will be an eventual guide for the test engineer to follow. So this is what I mentioned. When he do the PCB design, he needs to know where are the stray capacitance and what are the possible problems that he can face if he lay out his does his trace, maybe two traces too close together. You got stray capacitance effect, and how will that impact the test result? So the tester must be also, the tester is the main tool of the test engineer. Okay. So the test engineer must be very well versed with operating the tester, the resources in the tester, and the operating system or the software of the tester. Okay, so he needs to be able to develop test coding. So most of the testers today are in C++, in that kind of programming language. A lot of people, I think they understand C. And then the test engineer must be very familiar with oscilloscope. So oscilloscope, as you know, electrical testing, you cannot see anything. You don't know once something goes wrong, what's going on. In order to find out what's going on during electrical testing, you need to have a scope to scope out the voltages to understand what and where the problem is on your PCB. And then you need to be familiar with debug tools that is used in the tester. Debug tools are just like multimeter or oscilloscope that will reside in the software of the tester. Okay, you can bring this up and then you use those tools to find out what's going on certain tests. Okay, so this is an example of some of the test programs on the 93K and the 364. In JFTest sense, we have this tester. This is the programming environment. This is the 364 tester. This is the programming environment. When I said debug tools, this is an example of some of the tools that the tester has that you can use. You can debug timing, you can debug failure locations within a pattern, a digital pattern. You can debug the analog signals capture in time domain or frequency domain. Okay, so these are the debug tools usage expertise on the 364. Okay, so you have the display that shows you, it allows you to control during debug the voltage and the current ranges, how much voltage or current you want to force, okay, the measurement results and so on in real time. Okay, so as I mentioned, troubleshooting with scope is important. So this is typically a setup of a debug session in progress. You have the scope connected to the test PCB, and you're looking at all the signals to make sure that all is working well. On top of that, you need to have effective data analysis and troubleshooting strategy. Okay, so as I mentioned just now, you need to be able to analyze statistical data and understand the impact on the CPK, the sigma, the mean on the test results or on the yields. Okay, and then they use these results to find find out why the yields are low. Okay, so for example, this particular device lot has a lot of failures on this test, and you can see that the upper side limit, you can see that a lot of the parts are actually have a long tail. This distribution has a long tail and is skewed on the upper side. Okay, so that shows the CPK being very low. For standard CPK or process capability must be 1.33 and above, industry standard. For automotive standard is 1.67 and above, but normally we use this number 2. Okay, so this can be solved very easily by moving the upper side limit here, and that can solve the problem. Okay, your CPK automatically goes high. Okay, so now that you have seen the basic functions of a test development engineer and basic requirement or skills required from a test development engineer, do you have any questions?
Okay, thank you, Harjit. Any question? There's one from Fanis. What is CPK?
CPK is process capability. Is you can see here this is the formula where it's the upper side, the limit. You see, when we do every test, how do we judge whether the part fails or pass the test? It's based on limits that we apply. So the results or the measurement that we get from the device, we compare against a low limit and a high limit. If the measurement is out or lower than a low limit or higher than a high limit, is considered as fail. Okay, so the CPK can be calculated as the limit minus the mean of the distribution divide 3 sigma. Sigma is the distribution of the normal distribution. You have the parameter called sigma, right? So that upper side limit minus the mean divided by the 3 sigma will give you the CPK. And this number must be more than standard that we apply. Normally we apply 2. Okay, so that is CPK.
All right, thank you, Harjit. Any more questions on the students? Maybe we have other lecturers here as well. I can see Prof. Zahirul.
Assalamualaikum.
Yeah.
Okay, I can ask one thing. As per my understanding, that the PCB testing is very important for this type of testing.
Yes.
But as per my understanding, no university has the course for undergrad and masters for the PCB design. So how we can teach the student about the PCB design? Because the PCB design is completely a technical task, isn't it? So most of the universities don't have the course outline. Thank you.
Yeah, so you're right in the sense that PCB design is not part of any of the university course that I know today, but it's required for test engineering, for test development engineering. So what happens is that this skills is picked up during when the engineer joins the company. They will be given training on PCB design using maybe Cadence, or pads or whichever tool that is required by our customer.
Okay, thank you.
So they will learn the schematic design as well as PCB layout. That's done after they join the company, unfortunately. But maybe in the future we can think about implementing this in the university as well.
Yes, that's a good idea. Is there any like what do you call it, low cost software to design the PCB, because Cadence is expensive, right?
Yes, Cadence is expensive. There are actually a lot of low cost software that's available. I can share with you if you all want to know. We have actually our engineers here. They use low cost software. I'll let you know the what are the software names.
Okay.
If you want to know, and it's actually all free to use, but they have their limitation. So they can go maybe 2 to 4 layer. If you want to do more than that, then you need to use Cadence, Allegro, and so on.
I see. But it's good enough perhaps to study, to learn.
Yes, it's good enough for, yeah. In fact, our intern here, he used such a this low cost PCB software to develop just for his own training or his own understanding 4-layer board.
That's great.
Yeah. So, and then you just send the Gerber file that's produced from the layout, send it out to China, and then within 2 days you get your PCB back.
Oh, no, that's how fast. 2 days.
Yeah, and quite cheap also, just couple of $100.
Oh, really? Oh, that's great.
Yeah.
Okay, thank you. Any more questions? Anybody wants to ask more questions? There's one in the chat. What are the qualifications for an engineer fresh graduate to work in JFTest sense?
So we normally look for bachelors of electrical and electronic. Even a physics graduate also we will consider. Okay, so but you must have some prerequisite understanding of basic programming like C++, or Java.
Okay, but how about the CGPA? Is there any, I think the qualification there, is there a minimum CGPA for this?
I don't really look at CG. Of course, the first thing we look at is CGPA over 2.5 or something, or but even if it's the CGPA is above 3, the main thing I look for is the attitude. Are they really interested in electronic circuits and electronic circuit design, in software programming? These are the things that we look for. Doesn't have to be a genius or very good academically. So all that they can learn in the company.
Okay.
What I look for is good attitude.
Good attitude. Yes,
Okay,
thank you for that.
Okay, now so this is Zahirul Alam. So now some of the university, they shifted the programming language C++ to Python. So
Yes.
which is, I'm not sure. So why? Because the Python is IoT programming, and most of the university now they are moving towards that direction instead of basic programming, fundamental. So what is your comment?
So I think, as you said, Python may be applicable to other industries, like IoT, and it is actually catching on fast, especially among the young people. But people, in this particular industry, we do not have a tester that is running on Python so far.
Yes.
Our testers are mainly on C++, but I expect that, everybody has gone through some level of C++ programming as a basic.
Not sure, because nowadays everybody is shifting. So even they remove the course outline from C++ from the program.
Yeah. So
this is my worried. So they are also inventing Rust programming, Python, which is the fast growing and fast coming, and I'm not sure. So how long they will sustain. So this is so when something is new coming, so we jump without thinking.
Unfortunately, there are so many programming language there. So just because the Python is the most sexiest coding to do now, so people adopt that. But if you have done programming in one language, then going to another language is not a big problem.
Yes. But need to know how to do the programming. So instead of knowing the language, this is my strategy.
Yes. So you got to know what you are doing first. Okay, what you want to achieve.
Yes.
That's why the test plan is important. Then after that, it's just a language.
Yes.
Okay, thank you, Professor Zahirul and Mr. Harjit. Any more questions from the students or staff? Dr. Emilia also here. No question. Do you have a second part of your presentation or?
Yes. Yes, I can continue.
Please continue.
So now I'm going to talk about a bit more detail about the course that we have. The course that we have here in JFTest sense is called Fundamentals of Semiconductor Device Test Development. Now, this course is will guide the participant to test very basic devices, very basic IC, okay, like MOSFET, op-amps, NAND gates, read-write registers, uh, this linear regulators, linear voltage regulators, as well as switching regulators. So how do we deliver this courses is we have the theory portion. Okay, there will be a set of lecture that will introduce those particular device. Okay, what is the MOSFET? What is its function? What is its application? And then what is this? If you could take a data sheet, we'll go through the electrical parameters of the MOSFET, what they mean to the application, and then how they are tested. What is the test methodology adopted to test each of these electrical parameters? Okay. So once they've learned the theory, then they will go to the lab where they'll be given a lab guide to develop the test solution on one of the industry testers that we have in our lab called the Eagle 364. The Eagle 364 is a power management tester, and it's a C++ based tester, and the student will then need to create and develop those tests that's defined in the lab, the test list, and they will need to be able to just follow it. The lab is basically step by step, and they don't need to understand the tester. The lab itself will tell you how to create the test flow, how to create the test function, what tools to use, what to click and all that. But then in the end of the day, they will need then to debug what they have created to make sure that the tests are functioning. So during the debug process, they'll be using tools like oscilloscopes, digital multimeters, and so on. So there are about 6 modules in this course, where each module is a product. So first one is a MOSFET, and then op-amp, and then you have logic, and then you have the voltage regulators and the switching regulators. So the objectives is to introduce to automated testing, introduce the student into automated testing. As you know, semiconductor test development, we focus on automated testing or pulse testing. We want to instill these best practices of test development. We want to develop critical thinking and problem solving, and this happens when the students start to debug their new software and the hardware. They will develop a good foundation in basic analog and digital testing. Skills in using tools, for example, system tools, the tester tools, and external tools as well, the scopes and DMM. Okay. Then they acquire Eagle Test Systems 364 programming resource application skills. Okay, so this is the objectives. The lecture will focus on the theory of the device, as I mentioned, and then we cover MOSFET, op-amp, linear switching regulators, and logic. Then the data sheet, and then how to implement, and the theory of operation of tester instruments. So as we talk about how the test is done, we will come across, let's say, okay, now you will need voltage current source for this. Then we'll talk about, okay, what is the voltage current source? That will be explained during the lecture. Okay. So as far as possible, we try to explain the operations of the device or the those resources by using. So these are the modules, 6 modules. So module 1 is the basics or diodes and MOSFET testing. Okay. So what we would like probably minimum a week for this module. And then module 2 also another week for op-amp. Logic and digital device, module 3, and then voltage regulator. This is a low dropout regulator testing. Then you got switching regulator testing, which is a buck and a boost. And then finally followed by the synchronous read-write register testing. Okay, so 6 modules total for this fundamentals test development course. So what we suggest is 1 week per module, since we have only one machine. So during the labs, you can split the students into groups of maybe 2 or 3, and then they can take turns to use the tester and finish the labs in a week. Okay.
Are you speaking or my?
So the just is this their question?
Sorry, it was lagging. I thought because it was quiet for a certain time, so it's okay. It's just the internet, I guess. Please continue. Still lagging. Is it my internet or everybody can hear or just me?
I can hear you, Prof. Azlin, but I think, yeah, maybe Mr. Harjit, it's a bit lagging.
So Mr. Harjit's internet, so it's okay. Can you hear us, Mr. Harjit?
Maybe my internet is a bit. Oh yeah, I can hear my echo only now.
Okay.
Can you see the op-amp now? Or
Yes, we can.
okay, hopefully the lag is not too bad.
It's getting better now.
Okay, good. Okay, so as I said, I just want to show you an overview of the op-amp module, the op-amp course. For this, you know, the students, are you all familiar with op-amps?
The students, can you answer?
Yes, actually familiar, because it is actually under our course, also the lab class, both.
Okay, very good. So the students should be quite well versed and understand the op-amp. Okay, so you all understand that the op-amp we mostly consider, when you analyze an op-amp circuit, you consider op-amp as an ideal op-amp, right?
Yes.
Now, what is an ideal op-amp? Basically, you see here the ideal parameters of an op-amp, right? So it does not take any current at the input. The two inverting and non-inverting input has no voltage differential across it, is 0. Okay, ideal op-amp. The output resistance is 0, right? And then, of course, its gain, its open loop gain is infinity. Okay, by the fact that you have output voltage with 0 differential input, that already indicates infinity voltage gain, right? So when you apply an op-amp, you want any amplifier for that purpose, you only want to apply in the linear region of that device, correct? Because you don't want to apply when the device is in saturation at one level or the other, right? So the differential input of the op-amp, okay, so if the op-amp is not in feedback mode, meaning that you're just providing two sources driving the positive and the non-inverting and the inverting input, the output will only go to one level that's close to the positive supply, or the other level close to the negative supply, depending on the polarity of this input. If the positive or the non-inverting input is higher in voltage compared to the inverting, then the output will follow the non-inverting or the positive supply. And the reverse is true. You can see here, it's going from the negative supply going up to the positive supply, and the linear region is very, very small region here, and because it's like very high gain, so the useful region is very, very small. Okay, so most of the time the op-amp will be either here or here in the open loop condition. Do you all understand that? Because it takes very little differential for the op-amp to go and rail and be stuck to either the positive VCC or the negative VCC. Okay, so in this case, is the op-amp useful? In this way, the op-amp is not very useful, right? It is useful when it's set in a feedback mode. So a device which has very high or infinity open loop gain is ideal in closed loop. Why? Because we can control its output by just its feedback circuit. Okay, like shown here. You can see here, based on this, I think you've learned this in control theory, that the output voltage or the input voltage is inverse of the transfer function of the feedback circuit. That's all. You have the feedback circuit, and this actually will define the transfer function of the input to the output. Okay. So a very simple application of the op-amp we have is the follower board. And in test engineering, this is a very common circuit that we use in order to isolate the impedance of our device from the tester resource. Okay, because the device pin, which has probably high resistance, will see an infinite resistance. No current taken, right? Infinite resistance. So it's not good. You can't load a high resistance output device. Otherwise, that voltage that device produces will be low when it goes to a low impedance instrument, right? I will show that in a bit more detail. So, for example, if I have 5 volts here and I tie the output back to the positive input, what is V out?
Sorry, this type of problem and also this type of course already we have. So maybe most of the students know this one. They are actually know this the buffer amplifier, and the buffer amplifier input is very high, ideally infinity. So the input and output should be the same because it is a no. You are using which mode? Maybe your circuit is wrong. Maybe.
That is what I want them to tell me.
Yeah, because it is actually you cannot feedback to the inverting and non-inverting part. You must have to be feedback to the inverting part. That means minus sign is feedback and input is given to directly to the positive. That means it should be the circuit has some problem.
Yes, this circuit is, I purposely did it that way to test the student. This is
okay, sorry, I'm not the student, so maybe I give the answer. The student.
Yeah. So
sorry.
I was hoping for the student to tell me. So he'll tell me their level of understanding.
Okay. Mr. Harjit, our class, the session ends at 9:50, so I have 10 minutes. Maybe.
Okay, maybe I'll just rush through.
Okay.
Thank
you.
So for example, the application of this circuit, if this device has a high impedance, then you have a buffer in between to isolate the load. Otherwise, you will get half your voltage for this example. But if you put an op-amp in between, a buffer, okay, with the correct feedback to the negative input, then you get the correct signal, right? Because then you don't have a divider. what the source sees is a very high impedance. This is basically, in a nutshell, why we use buffers. So if I was ask you that how can we create a constant current source load here using that understanding, then it's very simply by applying this circuit, right? Where now I can control the current by putting an op-amp and a voltage source here and making sure that that voltage appears at this node so that the current is predictable and we can control the current value by controlling this voltage value. Okay, so since time is short, I'll just rush through. Okay, so as I mentioned, the feedback parameters, beta is the one that defines the forward function of the op-amp. In this case, this is a non-inverting gain circuit, okay, which is this. So you can see that a gain circuit is very easily realized by just choosing different values for the input resistance and the feedback resistance. Okay, so this is a very typical circuit that can be used for gaining voltages on our test circuit. Similarly here, okay, this is an example of how you can make a timestamp gain. Okay, then you have the inverting gain. In this case, the signal, if it's positive input, you will get a negative output, and the other way around. Okay. So in this case, if I got 5 volt at the input and I have a gain of -5, what will be the output, right? So the output will of course be saturated to -15. I can get -25 volt. Okay, so just this is another test. Okay, so now this is a circuit that we commonly use in some of our testing. If we require an I to V converter, I to V, current to voltage conversion, okay, where we just can measure voltage and derive the current based on this resistor. Okay. Similarly, this is also an I to V converter, but with a capacitor. Now this one timing is involved. So if I have a mechanism to measure the delta T of the voltage ramp that is coming out from the op-amp, I can derive the current. This is very typical test circuit that we use in bias current measurement of very low bias current measurement of op-amps in the region of picoamps or femtoamps. We use this type of circuit. Okay, so this is also one of our differential gain circuit. Okay, so you can calculate the differential gain. In this case, it's ×1, and you can modify the gain by just changing the feedback resistor. This is another application circuit. Now you have this problem where you have crossover distortion. So how do you eliminate that? So the solution is just move your feedback to the output. Okay, now when we design op-amps into our test circuit, or when we test op-amps, okay, during op-amp class there are two things. One is the application. Test circuits use a lot of op-amps for buffering, filterings, and so on. But we need to consider that when you actually apply these circuits or the op-amp circuits on your board, you must think about inductors or inductive effects of supply traces, and then how do you counter that, right? Inductive will cause noise because let's say your op-amp is have an input pulse train, then the supply currents will be switching. And because of the DI/dt and the inductance of the trace at the supply, there will be noise induced at output. How do you avoid this? Okay, I believe you all know, you all probably have developed op-amp circuits, and you know that when you develop op-amp circuits, It's a very common requirement or practice to implement decoupling capacitors. This will remove the noise caused by the trace inductance and switching currents.
Mr. Harjit, since we have a few more minutes, can we open for Q&A? I think I have questions, but I wonder if the rest will be. Can we? Do you have a few or many more or?
No. Let me just rush through the testing part. Okay, just cover this a bit. So during the lab, the students will need to create these parameters of the op-amp, and this is the data sheet of that op-amp that we are using, the LM158. And then they will use this tester to create the test solution. They will create the application duct hardware. This is basically the resources in the tester. The APUs are the VI, voltage current sources. And then this is the training board that we have developed for this course. And this is the tester kit in the lab for op-amp testing. Okay, you have the op-amp, you have the instrumentation amplifier to sense the input voltage, offset voltage. Those students will make to wire up this board to the tester resources, and then he will create a test plan like this, and he will develop the test code like this, and then debug it. You use the scope, and he needs to capture signals and qualify his measurements using the scope. Okay, so at the end of the course, we will give a certificate for successful completion for every student. Okay, so this ends my presentation. Any questions?
Thank you very much, Mr. Harjit. Any question from the floor first before I ask my question? Is there anybody, students or lecturers, want to ask questions?
Assalamualaikum. Again, I'm asking another question. In your, you teach the student for denoising, or maybe for the noise come from your pulse when input given, and denoising by using the decoupling capacitor. But when we use the op-amp for very low level of current measurement or voltage level measurement, you also mentioned in pico-ampere range as well. So,
Yes.
so the offset, that means offset is very important, because CMMR always not the same for all ICs, isn't it? So if the CMMR not same, and also the IC needs minimum biasing current, so how the student will know that the offset is very, very important if we measure very low level of current or voltage? It is not you mentioned in your discussion. I'm not sure. Maybe in your original course outline that is, or not. I'm not sure. This is my question.
Okay, that's a very good question. So, this is just a high level overview of the actual course. During the test development phase, the instructor will guide the student and tell them, look, when you use the instrumentation amplifier and measure the V offset, you need to calibrate out the CMRR effects as well as the V offset effects of those amplifiers used to measure the I bias or the V offset. Okay, because those op-amps that are used to make the measurements also have their own bias currents and the V offset, and this is taken care of during a calibration step, which is shown to the students. So that they will have an appreciation, oh yes, we need to remove those effects to get our measurement to be as accurate as possible.
Okay,
Thank you.
This is very important. You're right. I mean, in industry, these are some of the considerations that the test engineer need to have, and we need to actually deliver that understanding to the students during the lab.
Okay, I have a question maybe of interest to the student. What do you think? Do you think the country now needs more test engineers, or is it saturated in terms of the openings in the industry now? Can you comment on that?
Okay, so basically right now, Malaysia in the past 40, 50 years has been doing manufacturing, back-end manufacturing. So unfortunately, there's little has been done to move away or move up in terms of value provided by test engineers. So, but in the recent years, we have seen some companies that see that the benefit of having test development functions in this region, because first of all, the multinationals in Europe and US, they want to focus on new products. There is opportunity for the local plants here to develop new solutions for the old products that's already running. For example, if the old product has more demand, then somebody needs to develop a faster test time strategy or higher throughput strategy. So you need test development engineers, and that demand is growing. The problem is that we do not have good talent. We do not have enough good. I've been in the industry for 30 years. I've been looking for engineers to to help me.
Why do you say there's no good talent? What do you mean by good talent, Mr. Harjit?
There are no engineers that come in and say, hey, I was a test development before for 5 years or 2 years. It's very difficult to find. A lot of them, the good ones have already gone out of the country, either to work in the headquarters or to other higher paying companies.
Good means experience, you mean? Because I'm trying to understand. We say good. Do you mean experience?
Both experience as well as, because you see, the technical ladder does not exist in manufacturing plants. There's no ladder to say, okay, you're technically good, then you become a principal technical engineer or development engineer here. Because here everything is about production. Yeah, but in order for us to show the MNCs that we are capable, we need to, the first question they ask is, do you have good engineers for us to set up test development centers? If you want the MNC to come here and say, hey, they're looking for places to set up their IC design center. IC design center is where you can also incubate test development engineers. But then they're looking, where is the talent? Where are the students who are good in engineering, in electrical engineering, electronic engineering? I can tell you that many students that I've interviewed, they were very poor in their fundamentals.
Well, can you elaborate that? Maybe the student doesn't understand what you mean by poor in the fundamental.
If I ask them a question that if I source a DC current into a capacitor, please plot for me what the voltage looks like. How many students can do that?
Yes.
I've seen with my own eyes. I mean, I'm not complaining here, but basically that's the situation here.
Yes, I understand. Okay, there's a question by Dr. Emilia. The training is open for all. Where can I find the details on the workshop?
So this training is open for all universities. I'm looking forward to working with every university like yours also to implement this training in your degree course. Okay? So maybe it may not be an elective, but it could be embedded as part of the, maybe you teach the theory of the device and we can teach the testing. The problem now is that universities cannot afford the equipment.
Yes.
Right? They cannot afford the testers. So that's where JF is more than eager to help to facilitate the lab and teaching of this course.
Yeah,
so that the goal is for us to, why our vested interest is actually we want to grow my team. I want to grow my team here, so I need good engineers. So I'm using this path to find the cream of the crop and get them in.
Yes. So yeah, Prof. Anis and us, we will inshallah be working with JFTest and Mr. Harjit to plan to go over the course inshallah in the future, so the students can also anticipate for that. Any more question? I know the students have to go for another class. If you have another class at 10 o'clock, you can leave if you want. The rest, do you have any more question? I'm sorry, Mr. Harjit, because they have, maybe some of them have class at 10.
No, no problem. I'm so sorry for just dragging this presentation.
Mr. Harjit, this is my last question actually.
Yes.
What is your experience from the industry? The students' theoretical knowledge and also as the hands-on, which part they are actually more weak? Do you get my point? That means the hands-on means the practically very weak, or actually the theoretically weak, or both actually they are very weak. So we can.
Based on my 30 years of experience at the beginning, actually at the beginning of in the 80s and the early 80s, no problem. But now I see most of the students, they are weak in the fundamentals as well as the hands-on. I mean, when you ask somebody that comes in and do some basic soldering, not many can do. And if I,
we are puzzled because they do that in the university and suddenly they cannot do it. So the lecturers are puzzled.
Yeah. Yes. And if I show them an oscilloscope and then they are, also do not know how to use set the oscilloscope on trigger mode.
No, actually, oscilloscope is maybe student has problem because there are different model of oscilloscope and different types of oscilloscope. So sometimes in the new oscilloscope given to the student or maybe some expert, it is very difficult to handle if they don't know this one, because it is the instrument specific, isn't it? So if you given me your oscilloscope, maybe I'm not familiar with that type of model. So if the basic one, of course, they must have to know, isn't it? If you expect that one, that is correct. But if you expect a sophisticated some instrument like the oscilloscope, you test for the student, it is very difficult.
Well, I beg to differ on that, because when you teach oscilloscope, you teach the function. You don't teach a particular, you teach Agilent or you teach LaCroix. You teach the functions. So if they go to a different scope, they will be able to find the same function. It just take a bit more time.
Yes, but teaching the oscilloscope, it is actually different course as well. It is under the instrumentation or maybe instrument. But this is only the special course for masters, not for the undergrad. So students don't know the function, how the oscilloscope is basically work, because it's a very vast course.
Okay, now let me just comment. Because when we are using the analog oscilloscope, the student learn better. Now, when it comes to digital, the auto measure, just click that one instead of triggering all those. Just push the auto measure, just getting the digital display. There is no calibration. They don't know how to calibrate, because the analog, there are many functions need to do manually. So that is my feedback from this oscilloscope today's students mentality. So just measure it, just using the auto measure. So no need triggering, no need external also source of triggering also.
Yeah, I think one of the problem is that the university probably is not equipped well with the state-of-the-art oscilloscopes, and that could be not a big issue, because if they have operated an oscilloscope in the university, then the concept is applicable to any other oscilloscope, right? So it's something that they need to really have exposure on. While doing their degree, they should be exposed to whether it's analog or digital. Doesn't matter. The concept is the same. The concept is the same, right? So when they are seeing oscilloscope in the industry, they will be eager to independently learn how to use it.
Okay, thank you. Any more questions from the floor? I'm actually curious, Mr. Harjit, you were saying you have like 30 years of experience in the semiconductor industry. Can you share a bit, very short, I know 30 years is very long, your journey and why you are passionate in this for our students to keep them motivated? Can you share a bit?
After 4 years studying my E&E in University Malaya, I came out in 1987. And at that time, the industry was not as diverse as today. If you have studied electronics, basically it's only semiconductors. The only industry. There were no telecommunication. There were no other other industries at that time. So the thing is that what attracted me to the job was that it's the satisfaction that you get when you develop a solution, and the solution is not only software only, it also involves hardware. It can be mechanical pieces, mechanical parts that you need to design mechanical docking mechanism to dock your tester to the handler, the automated handler, for example. It also has software development aspects on it, the test program. It also has PCB design, test circuit design. So everything that works together, you always, as engineers, when you solve a problem and the problem is working well, or the solution is working well, then it's a satisfaction that you get out of it, isn't it? So that's basically, I saw that it's a very interesting field because you have so many aspects to it.
So which company have you worked before?
It's all basically multinationals, American mainly. I worked with National Semiconductor, today is Texas Instrument. And I've worked with also tester companies like Teradyne and Advantest. These are tester manufacturing and design and manufacturing companies. And also my last job was in 2017 before I joined JF with a company called Intersil, now bought over by Renaissance. So all the while it's with multinationals until today. Now I'm working for a Malaysian company.
Can we ask what's the motivation?
Motivation to work for Malaysian company?
Yes.
Because this is the opportunity where I have a chance now to develop talent. It's time for me to give back.
Yes.
I want to develop Malaysian talent. That's my goal now.
That's great. We hope that we can work together. That's our hope as well in the university, to develop more talent that can suit the industry, because we hear the mismatch, but we perhaps in the academia also we can learn how to equip ourselves and also our students. Okay.
Fantastic. Looking forward to that. Very good.
Great. Looking forward to that. Inshallah, Prof. Anis will arrange, I think, in the future for the co-offer of the courses. It's already 10:05. I think we should end this, or any one final question if there's any from the floor. Is there any? Okay, if not, I would like to thank very much Mr. Harjit from JFTest for your kind effort and time for being with here today. I think I learned a lot. I'm sure my students also learned a lot, and we hope we can work together in the future, and hope to see you again, inshallah.
Thank you very much. Thank you very much. All the best. All the best. Thank you very much.
Can we take a photo before we end? Can you stop sharing so we can take a photo? So everybody can turn on the camera, please. Let me see. How do I make it one screen? I cannot, so that we have 2 times to take photo. Okay, one screen. Okay, 1, 2, 3. Okay, done. Is that done? Okay, done.